Welcome to Chapter 5. In Chapter 4, you were introduced to the concept of random variables. Let's refresh. A random variable is simply a numerical description of the outcome of an experiment. So for instance, tossing a coin, the outcome is a random variable. You could denote heads as 0 and tails as 1. Hence, the two possible outcomes are 0 or 1, and they are described as numbers. Here in Chapter 5, we will be focusing on so-called discrete random variables. And in Chapter 6, we will be looking at continuous random variables. Here is how to think of discrete random variables. Think of numbers like 6, or 7, or 48, or 700,332,533. All those are discrete random variables. In contrast, a continuous random variable is something that can assume a value like 3.11 or 2.1125 or something like that. Here is another example of a discrete random variable, but this time it has a finite number of values. So pay close attention to this. So for instance, in the appliance store, the number of TVs that can be sold is a random variable. It depends on whether it's a good day or a bad day. Sometimes they can sell as few as 0 TVs, and sometimes as much as 4 TVs. So here is the important thing to note. The possible outcomes are all discrete numbers. But the range of values is finite. Only 5 possible values, from 0 to 4. But be careful, because there are sometimes some discrete random variables that can have an infinite sequence of values. So, number of customers. Theoretically, an infinite number of customers could arrive. It's just that in practice it won't happen. But it's just that, be careful. In this case, the sequence of values is potentially infinite. So let's do a brief survey. Hence, family size. That's a discrete random variable because you can't have 3.5 members of the family. You can have only 2 or 5 or 7. In contrast, the distance from the home to store is a continuous random variable because it could be 3.11 miles or 0.712 miles and so on. And here's another example on the third row where you create a variable depending on whether one owns a pet at all or whether one's own a dog or a cat or both a dog and a cat. As you can see, this is discrete. Now, what's nice with so-called discrete probability distributions is that these are formulas or equations that simplify our task in analyzing discrete random variables. Remember, a random variable has a probability attached to it. One way you could analyze a random variable is by drawing tree diagrams or doing multiplications and so on. But that's going to be tedious. The nice thing is that there are some phenomena in nature which can be described by probability functions. Just a brief review. The probability of any outcome is greater than or equal to 0. And the sum of the probabilities of all outcomes should be equal to 1. And that's exactly what a probability distribution function does, or a probability function. It's a box, it's a formula where you put in an outcome, 3, and out pops out what is the probability of getting 3. And of course, if you exhaust all possible outcomes, all those probabilities that have been spat out should add up to 1. Let's look at the appliance store example again. So, note this, using past data on TV sales, this is what we observe as the probability distribution of the number of units sold. So you will see in 80 of the past 200 days, no units were sold. In 10 of the past 200 days, 3 units were sold. So you will see in the other box, we now compute the relative frequencies of these possibilities. Now, what it all boils down to is that you can consider these relative frequencies as also the probabilities for each possible number of units sold. Remember this approach? This is the so-called relative frequency approach, which was described in Chapter 4. And this is the graphical version of the appliance store's possible sales of TVs. So the way to interpret this is there is a 40% chance that no TVs will be sold. That's the point 4. There is a 5% chance that 3 TVs will be sold on that day, and so on. Now this is a case where we use observation or past data in order to construct a relative frequency. We will now move into more general probability functions. But first, take note of these concepts, which we discussed in Chapter 3. Let's first start with the so-called discrete uniform probability distribution. And this is the simplest example. What this just means is that each outcome is equally likely. Hence, consider, for instance, tossing a die. There are 6 possible outcomes, right? 1, 2, 3, 4, 5, 6. Each one is equally likely. Hence, the probability of each outcome is exactly 1/6, or 1 divided by the number of possible outcomes. So what is the probability of getting 3? It's 1/6. What is the probability of getting 2? 1/6, and so on. Now recall the concept of expected value. In the case of a random variable, we can also calculate the expected value or mean of a random variable. The way to think of this is it's just a weighted average of the values the random variable may assume. Another way to think of this is toss a die for, I don't know, 5,000 times. Write down the outcome each time. You'll have a sheet of paper with a lot of numbers. You could group the data. You could create relative frequencies and so on, and you could calculate the mean of the data of the 5,000 numbers on the sheet. That is exactly the expected value. Be careful. As I've noted in red, the expected value does not have to be a value that the random variable can actually assume. And here is a real-life example, tossing a coin. What is the expected value? Think of it this way. Suppose you assign 0 to heads and 1 to tails. Keep tossing a coin, let's say 5,000 times. You'll have a sheet with 5,000 numbers consisting of zeros or ones. Take the mean of those 5,000 observations. In practice, you will get something close to, think for a minute or two. Yes, the expected value will be 0.5. So that means that over time, the expected value of tossing a coin is 0.5. But in real life, you will never get half a head or half a tail. And therefore, the value will always be either 0 or 1. Similarly, the variance and the standard deviation can be calculated for a discrete random variable. These definitions are just copied from Chapter 3. So let's consider again the example of the appliance store. And this table just shows the relative frequencies. In the second column, the third column multiplies each outcome by its respective relative frequency. And as you can see, the sum of those products is just the expected value. So how we interpret this is that on average, the appliance store can expect to sell 1.2 TVs in a day. Of course, it's never going to sell 1.2, right? It's going to be 1 or 3 or 0. It's just that on average, it will sell 1.2 TVs. Similarly, we can compute the variance. And please take a minute or two to analyze this table. The first column is just the list of outcomes. The second, we just subtract the mean from the outcome and the mean which we've computed in the previous page. In the third column, we square the difference. And in the fifth column, we multiply the squared difference by the relative frequency. The bottom row is the variance, which is just the sum of all the squared differences. Please note, what did we divide this by?